In the last lecture, we saw that even though both the 3D and 4F electron systems, namely the iron group and the rare earth group of paramagnetic ions, both have similar outer electron structure, still there is a big difference in their magnetic behavior. For example, if you measure the magnetic susceptibility and try to relate it to the Brillouin function expression for the paramagnetic susceptibility or the magnetization, you find that there is very good agreement between the calculated values and the theoretical values in the case of the rare earth ions, the 4F ions, whereas the agreement is rather poor in the case of the 3D electrons. Now, we would like to spend some time trying to understand this reason for this difference in behavior between 4F and 3D electrons in the unfilled shells. We know that in the case of the rare earth ions, the 4F electrons have outer phi s and phi p electrons, 4F electrons surrounded by whereas in the case of the 3D electrons, there are no electrons outside and they are the outermost electrons. So, this is the rare earth group and this is the iron group. So, the 3D electrons lie outermost, whereas the 4F electrons are protected from outside influence, relatively isolated because of the presence of the outer phi s and phi p electrons. Therefore, they shield the 4F electrons from the influence of neighboring electric charges, whereas in the iron group compounds, the 3D electrons are the outermost ones and they are considerably affected by the presence of neighboring electric charges. And usually in all these compounds, the paramagnetic ion is surrounded by what are known as ligands, such as O2 minus or SO4 2 minus or and so on, H2O, etc. These are the ligands which are present, which surround the paramagnetic ion, and the reason because such electric charges are present, they produce crystalline electric fields at the site of the paramagnetic ion. So, the paramagnetic ion, the behavior that we saw regarding the ground state of this is affected to a large extent by the presence of these crystalline electric fields, and this results in a stark splitting of the ground state. As we know that the magnetic behavior is profoundly affected by the ground state of the paramagnetic ion, because for statistical reasons it is the ground state which is mostly occupied by most of the ions. Therefore, the magnetic behavior is almost completely determined by the nature of the ground state, and since this ground state is split by the Stark effect due to the crystalline electric fields produced by the ligands. Therefore, the nature of the paramagnetic ground state is different, and therefore, the magnetic behavior is also considerably different in the case of the iron group ion. To see this effect, let us consider for simplicity a p state ion. D is a little complicated. So, let us just take an ion which has p electrons in the p shell, which consists of 3 orbitals which are known as the px, py, pz orbitals, which are shown in the next figure. So, the lobes of these orbitals are directed along the x, y and z axis. These are shown in the figure. Now, you see also in this figure charges or the ligands being shown. These ligands surround this ion, and some of them are positive and some of them are negative. So, in the free ion, all these 3 are degenerate. But now we have an ion which is not free, but is subject to the crystal electric fields. So, because if this ligand has a negative charge, next to the electronic cloud, then the electron cloud will be repulsed by this negative charge, and therefore, the energy of this particular state will go up, it will be increased. Whereas, if it is, then energy is increased. Obviously, if it is a positive charge, the energy will be lowered. And if there is no charge or is it neutral, then nothing will happen to the energy. So, if you see the px electron, if you consider the orbitals shown in the figure, one finds that the py orbitals have positive charges. So, the py orbital will get lowered. So, to start with, the px, the py and the pz are all together in the free ion. Now, this degeneracy is lifted by the free ion. The crystalline electric field lifts this degeneracy due to the ligand, and therefore, the py gets lowered, the px gets increased and the pz remains the same for the configuration that is shown in the figure. So, the presence of the ligand lifts this degeneracy and makes all these 3 energy levels separate, and therefore, the ground state has become a non-degenerate ground state. Whereas, this is a degenerate ground state. The consequence of having a non-degenerate ground state can be readily seen from the Schrodinger equation, that a non-degenerate ground state, any non-degenerate quantum mechanical state, is represented by a real wave function. If the wave function is real, then the z component of the angular momentum is represented by minus I h cross d by d phi in a spherically symmetric atom. So, this is L z, and therefore, this is an imaginary operator. So, if you have an imaginary operator with a real function, this will be 0. So, the eigenvalue will be 0. So, the eigenvalue of Lz vanishes for such a system, and therefore, the paramagnetic moment is identically equal to 0. So, the orbital angular momentum for such a state is said to be quenched. So, this is a very famous phenomenon, namely that of the quenching of the orbital angular momentum by the crystal field. Crystalline electric field of the ligands. So, when the orbital angular momentum is quenched, it does not any longer contribute to the magnetic moment, and we have only a spin only magnetic moment. We have already seen that the magnetic moment arises from two contributions, one due to the orbital angular momentum, another due to the spin angular momentum. Because the orbital angular momentum is quenched physically, this means that the crystal electric field keeps the paramagnetic ion locked, and therefore, it is unable to reorient in the applied magnetic field. So, there is no contribution to the magnetic moment from the orbital state. Therefore, it is only the spins which contribute to the magnetic moment. Whereas, in the case of the rare earth compounds, even though the crystal field is not 0, but its effect on the ion is not as strong as in the case of the ion group, because of the shielding of the 4f electrons by the outer phi s and phi p electrons. So, this is the reason why the paramagnetic behavior of the iron group ions is only due to spins. If we went to the table which showed the magnetic moments, calculated and experimental values of the magnetic moments of the rare earth and iron group ions, we will see in this table that, for example, if we consider an ion like Mn3 plus, you see that the experimental value of the magnetic moment is 4.9 Bohr magneton, whereas the value calculated from assuming that the total angular momentum is j is exactly 0. So, there is no comparison between the experimental and theoretical values, whereas if you consider the spin only contribution, then the magnetic moment is equal to 2 twice s into s plus 1 to the power half. Therefore, that calculated value comes to be exactly the same as the experimental value, 4.9 Bohr magnetons. Whereas, in the case of the rare earth ions, there is very good agreement between the experimental and calculated values on the basis of the assumption that the total angular momentum j is the resultant of L and S. That is, both orbital and spin contributions exist. So, this is the main difference between the rare earth ions and the iron group ions. Next, we pass on to a very important topic. The entire problem of magnetism is of interest for practical reasons only because of the existence of the phenomenon of ferromagnetism. Paramagnetic moments as well as diamagnetic moments are extremely weak and they are barely perceptible in ordinary experiments. It is only because of existence of ferromagnetic materials such as cobalt, iron and nickel that there is a lot of current interest in magnetism as a phenomenon with respect to practical applications as well as theoretical explanations. So, what is ferromagnetism? In the case of ferromagnetism, we recall what happened in the case of the dielectric materials. We had noted that under the presence of the Lorentz internal field in a dipolar solid led to the phenomenon of ferroelectricity under certain conditions. Very similar to that, the ferroelectric phenomenon meant that there existed a spontaneous polarization. In other words, the dielectric gets polarized even in the absence of an applied electric field in the case of a ferroelectric material. Similarly, in the case of the ferromagnetic material, the magnetic material shows magnetism even in or a magnetization even in the absence of an applied magnetic field. Even if you have a piece of iron which has been magnetized, then even when you do not have an applied magnetic field, even if you keep it like this, a piece of iron, it will attract another bar magnet, showing the magnetic effect. So, you do not have to apply a magnetic field in order to produce this. So, there is already a spontaneous magnetism present in such a ferromagnetic material. This is not there in the case of diamagnets. In the case of the diamagnets, the magnetization is present only as long as the field is applied. It vanishes when the field is removed. In the case of the paramagnetic moment, this is not the case. There is a net magnetic moment in the presence of the field, which is proportional, which increases with the magnet strength of the applied electric field until you reach saturation. But still the magnitude of this effect is very weak in comparison to a ferromagnet. So, Weiss postulated the existence of a molecular magnetic field whose strength is proportional to the magnetization in order to account for the observed temperature dependence of the paramagnetic susceptibility at high temperatures in a ferromagnetic insulator. So, this is what we are going to consider now. So, the Weiss molecular field hypothesis. This molecular field is very similar to the Lorentz internal field in a dielectric. So, this is hypothesized, and this molecular field, the strength of this is proportional to the magnetization. This was the hypothesis by Weiss in order to account for the observed temperature dependence of the paramagnetic susceptibility of such a material at high temperatures. Now, how does the paramagnetic susceptibility of such a ferromagnetic insulator depend on the temperature? We have already seen that in the case of a paramagnet, this paramagnetic susceptibility equals C by T, where C is the Curie constant. So, if I plot the 1 by chi versus T, this product is a constant. So, we are going to get if I plot chi versus T, this is going to be a hyperbola, rectangular hyperbola. But if I plot 1 by chi against temperature, then this is going to be a straight line, because 1 by chi is proportional to T, it is T by C. So, this is a straight line through the origin with a slope equal to C or 1 by C, 1 by the Curie, the reciprocal of the Curie constant. So, this is the behavior in the case of the ideal paramagnet, but this is rarely observed in practice, because there is no material which remains paramagnetic down to the lowest temperatures. At some low temperature, which is low enough, there is a ferromagnetic order. As you will see, ferromagnetism is because of an ordering of the magnetic moments. So, the ferromagnetic order sets in at some temperature known as the Curie temperature. Appears at what is known as the Curie temperature. We indicate it by theta, in which case the chi versus T behavior of such a ferromagnet, rather the chi inverse versus T, is not a straight line through the origin, but it is a straight line with an intercept on the T axis, and this intercept is has the value theta. Its slope is still 1 by C. In other words, chi is C by T minus theta. So, this is the for the temperatures greater than the ferromagnetic transition temperature or critical temperature Tc. So, the paramagnetic susceptibility obeys a variation of the kind C by T minus theta, and below this temperature for T less than Tc, as we have already seen, ferromagnetism sets in and we have a spontaneous magnetization. That is, we have a magnetization, non-zero magnetization below Tc, even when there is no applied magnetic field. Therefore, in principle, the magnetic susceptibility, which is the ratio of these two, the magnetization to the applied field, should diverge. So, this is very similar to the polarization catastrophe in the case of a ferroelectric. So, we can write this molecular magnetic field, since it is proportional to the magnetization, we can write it as B molecular equals lambda m, where lambda is a constant known as the molecular field constant. So, now we have m equal to C by T times B, that is the well known behavior of the magnetization. But now the B is not what you have applied, but it is the sum of the B applied plus the B molecular. Therefore, this is C by T into B applied plus lambda m. Since I have terms involving the magnetization m on both the left and right sides of this equation, we will bring it together and write m into 1 minus C by T into lambda equals C by T into B applied. So, m by B, which is chi in the linear region of the response, is C by T into 1 minus lambda C by T, and that is equal to C by T minus lambda C. So, lambda C equals theta. So, we are able to account for, using the molecular field hypothesis of Weiss, we are able to account in a very simple way to the for the existence of the Curie-Weiss temperature. Theta is known as the Curie-Weiss temperature. So, the molecular field hypothesis accounts in a rather simple way, straightforward manner to for the variation, experimentally observed temperature variation of the paramagnetic susceptibility at temperatures above the ferromagnetic Curie point or transition temperature. So, this is what we have seen, and now we would like to use this molecular field hypothesis to develop a criterion for the existence of ferromagnetism using the theory that we have used already. So, let us do this now. So, we have, according to the theory, M is N G J mu B, B J J into B J of x. N G J into J mu B into B J of x, where B J of x is the Brillouin function and x is G J mu B, B by K B T. And since we know that in the absence of an applied magnetic field, this will simply be G J mu B lambda m, which is the Weiss molecular field, by K B T. So, we have already one equation governing the magnetization, and now this gives me another equation for the magnetization by inverting this. So, this is going to be K B T by G J mu B times x. Lambda. So, I have two equations now for the magnetization in this case. One according to the well known Brillouin function dependence, which we derived earlier in the last time, and we also have another relation for the magnetization via the molecular field. So, both of these have to be satisfied when there is such a Weiss molecular field present. So, we have to solve both these equations simultaneously in order to obtain a solution for the magnetization. So, we do this graphically by means of a graphical method. So, if we plot this Brillouin function, we are going to get m versus x is going to be a Brillouin function dependence, which we have seen already. So, this is m naught. In addition, we also have a linear relation between m and x given by this equation, by equation 2. So, this is going to be a linear relation. So, this is 1, this is 2. So, the graphical method involves the simultaneous presence of these two. So, the graphically the intersection of these two graphs gives you the magnetization. So, this is the situation, but as I see, as we vary the field or the temperature in this case, we see that slope of this graph changes, and so we have successively straight lines like this. So, eventually a situation is reached when the straight line touches this Brillouin function graph at the origin. So, a simultaneous solution of 1 and 2 is not possible for values of the temperature which are such that it goes beyond this. So, the straight line is just tangential at the origin to the Brillouin function graph at the transition temperature. This point is defined as the point at which the transition takes place. So, above this, when there is a simultaneous solution for these two equations, then you say that there is a spontaneous magnetization and there is ferromagnetic order present for temperatures below this point. Therefore, for these the slope is such that, so you have situations like this is T greater than T c and this is T less than T c, and this corresponds to T equal to T c. So, the ferromagnetic Curie point is defined by this simultaneous solution as the point at which the linear graph is tangential to the Brillouin function. Since we know the slope of the Brillouin function expression at the origin, we can equate the slope of the straight line and the slope of the Brillouin function in order to obtain this ferromagnetic Curie point. So, this is what we do. So, at the origin, the slope of this is j plus 1 by 3, that is the slope at the origin, and that will be equal to this kb Tc by Gj mu b lambda. So, that gives the expression for Tc. So, we get Tc as Tc equal Gj mu b j plus 1 into lambda by 3 kBt. This is really j into j plus 1 by 3. And we know Gj mu b into j plus 1 by 3 kb is our effective magnetic moment, and therefore, this is, if this ferromagnetic Curie temperature is the same as the Curie-Weiss temperature, then this is lambda c equal to theta. So, this tells me, since the Curie constant is just this, therefore, this is just c lambda c. So, this just says that the Tc, the ferromagnetic Curie temperature, is the same as the Curie-Weiss temperature according to the molecular field theory of a ferromagnet. Of course, all this is very nice. Phenomenologically, it gives a very nice explanation for all the observed facts of paramagnetism and a simple ferromagnetic material. But still, we are left with the basic question of what is responsible for the existence of such a molecular magnetic field. The Weiss hypothesis remains a hypothesis, it does not address this question, because the molecular field, as we will see, is basically of a quantum mechanical origin. So, it needs a quantum mechanical explanation to understand why this molecular field arises in the case of an ordered ferromagnetic material. This quantum mechanical molecular field is known as the exchange field. for reasons which we will see. So, this is arises from what is known as the exchange interaction. So, next we will deal with the exchange interaction. So, the exchange interaction was proposed, the theory of this was proposed by Heisenberg. So, it is known as the Heisenberg exchange interaction. So, this is the one, this interaction is responsible for this molecular field diagram. In order to understand the origin of this exchange mechanism, we have to consider the theory of covalent bonding of a homonuclear diatomic molecule such as hydrogen, which was originally proposed by Hitler and London. So, if you take hydrogen molecule, which consists of two hydrogen atoms which are bonded together, and the nature of the bonding is that they share the electrons and form what is known as a covalent bond. Hitler and London considered this model of a diatomic molecule, homonuclear diatomic molecule like hydrogen, and stated that the electrons are shared between the two bonded atoms, so that a given electron belongs with equal probability to either of the two atoms. So, we can write the two electron wave function of such a state as the two electron wave function is written as, since it involves two electrons, let me write electron 1, electron 2. So, this will be 1 by root 2 psi a 1 psi b 2 plus psi a 2 psi b 1. What is the meaning of this? When I write, it can be plus or minus. In other words, you have two combinations, linear combinations of the individual atomic wave functions. They are known as psi a 1 and psi b 2. Psi a 1 means electron 1 is belongs to atom A. In the hydrogen molecule, we have two atoms, two hydrogen atoms, one is called A, another is called B. So, we can have the electron 1 sitting with atom A and then the electron 2 sitting with atom B. So, such a state is called psi a 1 for the electron 1 and psi b 2 for the electron 2. So, the total electron wave, two electron wave function is a simple product of these two. So, it is psi a 1 psi b 2. But as the model says, the two electrons can be shared by the two atoms, and therefore, a given electron can belong with equal probability to either of the two atoms. So, it is not necessary that electron 1 should be with nucleus A. Instead, electron 1 can also belong to nucleus B, and electron 2 will then belong to nucleus A. So, in this case, the two electron wave function, product wave function will have the form psi a 2 psi b 1, and the model says both these wave functions psi a 1 psi b 2 and psi a 2 psi b 1 are equally probable. Since it is only the mod of the psi square which is related to the probability and therefore has any real significance. So, we can have this equal probability represented by either a symmetric linear combination of these two functions corresponding to the plus sign here, or an antisymmetric. So, you have a symmetric linear combination or antisymmetric linear. The antisymmetric combination corresponds to the negative sign, because if you interchange them it changes sign. So, it is antisymmetric with respect to exchange, that is why you call it an antisymmetric linear negative sign. If it is a plus sign, it is symmetric. If you exchange it, nothing happens, the sign remains the same. So, it is symmetric with respect to exchange. So, you have a symmetric linear combination as well as an antisymmetric linear combination. Both are equally valid wave functions for the 2 electron system. This is what you have to use in the Schrodinger equation for the hydrogen molecule. So, next step in writing the Schrodinger equation is to write the Hamiltonian, so that we have H psi equals E psi as the Schrodinger equation. That gives you the, this is the Hamiltonian operator operating on this wave function, giving rise to the energy eigenvalue, in which what we are interested. We are interested in the basic question, why is the ground state of this molecule lower in energy? Why is the energy is lowered by the bonding, by the formation of the molecule? Instead of being 2 separate atoms, why does the 2 atom system prefer to form a molecule? The answer is that it is because the molecular configuration is lower in energy and therefore has greater stability. So, we have to find the energy, which means that we have to solve the Schrodinger equation, which involves the Hamiltonian operator. So, we have to next consider the Hamiltonian of this 2 electron system. So, the various terms are P1 square plus by 2m plus P2 square by 2m, which is the, which are the kinetic energies of the 2 electrons. So, I have 2 nuclei and 2 electrons. So, what is the energy? Now, these are electrons and these are positive nuclear charges. So, there are electron repulsion terms. Now, this can be corresponding, this is one possibility, another. So, you have various interactions possible now. So, the nuclei repel as well as the electrons repel. So, you have various distances which will determine this repulsion energy plus Coulomb repulsion of electrons and nuclei as well as nuclei, plus Coulomb attraction terms between electrons and nuclei. The attractive terms are negative and the repulsive terms are positive. So, the attractive terms, for example, are minus E square by 4 pi epsilon naught. Since it is a hydrogen atom, you have a 1 electron and a nucleus of charge equal to the electronic charge. So, I have minus into 1 by R A 1, that is the distance between A and 1, and then so, these are all attractive because it is between nucleus A and electron 1, and then nucleus B and electron 2, and nucleus A and electron 2, and nucleus B and electron 1, all of which are attractive terms. So, you have 4 such terms, whereas the repulsive terms, which are positive in sign, are plus E square by 4 pi epsilon naught times 1 by R12 plus 1 by RAB. So, these are the distances between the two nuclei RAB and the two electrons R12, both of which are repulsive. So, all these terms enter into the Hamiltonian, and we use this Hamiltonian and this 2 electron wave function to solve for the eigenvalues of the molecular state, ground state, and that will give us a clue for the presence of the exchange interaction. We will consider the solution in the next lecture.